So this video will cover the solutions to the second set of tutorial questions for PHYS9120. So this is question 1 here, where we've got a velocity versus time graph. And in part A of this question, we're asked what distance has the object travelled over the 10-second time interval. So the distance travelled is equal to the area under a velocity versus time graph. So when we're asked to calculate the distance, the area under the curve on top of the zero line counts as positive, as does the area underneath the line. If we were asked to calculate the displacement, then the area under the curve on top of our origin line would count as a positive number, and the area below the origin, the x equals 0 line, would count as a negative number. So they'd subtract from each other for the displacement, whereas they add for distance. So to answer this, we're just going to need to work out the area under this curve. So to do that, we can divide it into some simple shapes. So let's start with this rectangle here. It's got a length of 3 and a height of 1. So that is a distance of 3 meters. We've then got this trapezium here. Now the height of this side is 1 and the height of this side is 4. So the average height, 1 plus 4 on 2, and then we times it by the width, and it's got a width of 2. So we can see that those 2's will cancel, and we've got 5 meters traveled in this time interval. Now going from 5 to 6 seconds, that's just a triangle with a height of 4 and a length of 1. So the area of a triangle is half the base times the height. So that is 2 meters in this case. Between 6 and 7 meters, it's got 0 velocity, so it's not going anywhere. So the distance it travels is 0 meters. And then we've got this triangle here between 7 and 10. So that's got a length of 3 and a height of 3. So half of 3 times 3 is 4.5 meters. So if we want to get the total distance, we just need to add all these up. So that's 3 plus 5 plus 2 plus 4.5. And when we add that, we get 14.5 meters. Part B then asks us, what is the instantaneous acceleration of the object at 4 seconds? So that's asking us to find the acceleration of the object here. So to get instantaneous acceleration, it's equal to how quickly the velocity is changing at that instant, which is just the gradient at the instant. So we need to find the gradient here. So we can see this is just a slope. So the gradient of a slope is given by the rise over the run. So this is equal to the change in height. So we're considering these 2 points here. We'll find the gradient between these 2 points. So the final height is 4. The initial height is 1. The final x is 5 and the initial x is 3. So this is equal to 3 over 2, or 1.5 meters per second is the acceleration at 4 seconds. Part C then asks, what is the average acceleration of the object over the 10-second interval? So for average acceleration, we do the total change in velocity over the total change in time. So the final velocity minus the initial velocity over the final time minus the initial time. The final velocity, that is this value here, and the initial velocity is this value here. So we can see the final velocity is minus 3. The initial velocity is 1, so minus 1. The final time is the 10 seconds and the initial time is the 0 seconds. So this is equal to minus 4 over 10, which is equal to minus 0.40 meters per second is the average acceleration. Now part D asks us to plot a displacement versus time graph for the object over the 10-second interval, and we're asked to include a description of the shapes of the lines that we've drawn, and we should also include numeric numbers on our axes. Okay, so let's put displacement up here, and we'll put time along here. So we'll start at 0 and we're going up to 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and we'll work out what's happening along each of these time intervals. So between 1 and 3 seconds, it's got a constant velocity. So if it's got a constant velocity, that's going to be a constant gradient on our displacement graph. And that constant gradient is going to be equal to the velocity, so constant gradient of 1. So we're told that it starts at the origin, so we know it starts here. And then at 3 seconds, we've already calculated that it's traveled a distance of 3 meters. So just before we start, let's work out what would be sensible numbers to put along our displacement axis here. So the total displacement is going to be, over the 10 seconds, will be the 3 plus the 5 plus the 2, which gives us 10, minus the 4.5, which should be 5.5. But the maximum displacement is going to occur at 6 seconds, because that's when it turns around and starts coming back. So the total distance traveled up to 6 seconds is the 10 meters. So if we go up to 10, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, we should be able to fit everything on. Okay, so at 3 seconds, it's traveled 3 meters, and it's done that with a constant gradient. So it's asked us to label these. So this is a straight line. And now between 3 and 5 seconds, the velocity is changing at a constant rate. So we've got a constant acceleration. So between 3 and 5 seconds, constant acceleration. So when something's accelerating, it's going to have a parabolic shape. Now we know that at 5 seconds, the total displacement is the 3 plus the 5, so 8 meters. So at 5 seconds, we've gone up to here. And as we've said, this is a parabola. It's going slower at the start and faster at the end. So we've got a parabola like this. So this is a parabola. This is why it's important to label it, because it's not necessarily easy to draw it very accurately. Now between 5 and 6 seconds, it travels an extra 2 meters. So then at 6 seconds, it's got to 10 meters, but you can see in this case the velocity is decreasing. So again, it's going to be a parabola, but in this case the parabola is going to be going the other way. It'll be steep and then it's going shallower. So between 5 and 6 seconds, constant acceleration, and a parabola again. But at 6 seconds, the velocity is 0. So that means that here, the tangent to our parabola is going to be a straight horizontal line. So we've got another parabola here. And then between 6 and 7 seconds, there's no displacement. So it's not moving. So that's a nice straight line between those two. Then between 7 and 10 seconds, it's now going faster and faster, but in the negative direction. So at 10 seconds, it's traveled a distance of 4.5 meters back towards the origin. So that'll be 10 minus 4.5, which gets us to 5.5. So this is at 5.5. And again, it's going to be a parabola, and it'll be curved like this. So it's steeper at this end and shallow up here. So between 7 and 10 seconds, another parabola. Okay, so that is a sketch of what the displacement versus time graph is going to look like. So this is question 2. So in this one we have to complete a table, and in the first row of the table we're told that the displacement vector is given by 1.0 ti minus 2.3 t squared j plus 4k. And the first thing that we need to work out is, well, what's the velocity? And so to get the velocity from the displacement, we're just going to need to use that the velocity is the derivative with respect to time of the displacement. So we're going to want to differentiate this with respect to t now. So we'll do each of the components separately. So when we consider 1t in the I direction, when we differentiate this, we end up with 1, and that's still in the I direction. When we differentiate 2.3 t squared, we end up with 2 times minus 2.3, which is minus 4.6, and then this becomes a t instead of a t squared, and that's in the j direction. And then we've got 4k, that's just a constant, so when we differentiate that, that becomes 0. So this is our expression for the velocity. For the acceleration, we need to use that the acceleration is equal to dv dt. So what we're going to do now is differentiate this velocity with respect to time. So in the I direction, we've just got a constant. There's no dependence on t there. So when we differentiate that, that is just 0. So now we're differentiating minus 4.6t in the j direction. So that's just minus 4.6, still in the j direction. We're then asked what is the displacement at t equals 0. So for that, we just have to substitute in t equals 0 into these terms. So you can see in the I direction, because there's a t there, this is just going to be 0. In the j direction, again, this is just going to be 0. And because this one's constant, this one here will remain the same. So this will be 4k. And we're also asked what's the velocity at time equals 0. So now that we've got our velocity expression here, we're just substituting in t equals 0. So that will make this term here disappear, and we'll be left with the 1.0 in the I direction. Part B, we're told that the velocity is equal to t squared I plus 3j minus 4t k, and we're also told that at t equals 0, the displacement equals 0 at t equals 0. Okay, so we need to find the displacement. So to get displacement from velocity, we need to integrate it. So we're going to be integrating the velocity with respect to time. So we're doing the integral of t squared I plus 3j minus 4tk, and all of this is with respect to time, so dt. So when we integrate t squared, we end up with t cubed on 3, and that's in the I direction. And then we're integrating 3j, so when we do that, we'll get 3tj. And then when we integrate minus 4t, that becomes minus 4t squared, and then we're dividing by 2, and that's in the k direction. And then because this is an indefinite integral, we don't have limits on this integration, we've got a constant of integration. So what we're going to need to do now is find this constant, and to find this constant we'll need to make use of the fact that s equals 0 at t equals 0. So we'll substitute in t equals 0, and then we know s equals 0. So we've got 0 is equal to, well, when t is 0, this term's 0. This term is also 0. This term is also 0, so that's equal to our constant. So we know this constant of integration is equal to 0. So we can simplify this expression a bit then. We've got t cubed on 3I plus 3tj, and then 4 divided by 2 is 2. So that's minus 2t squared k. So that's our expression for the displacement. Now, we were also asked to find the acceleration in this case, so that's a little bit easier. We can just differentiate the velocity with respect to time. So we're differentiating this expression here. So when we do that, we differentiate t squared, that is 2t in the I direction. When we differentiate 3j, that's a constant, so that's just 0. And then when we differentiate minus 4t, we get minus 4, and that's in the k direction still. So that's our expression for the acceleration. And then we've been told the displacement at t equals 0, and we have to find the velocity at t equals 0. To get the velocity at t equals 0, we're just substituting t equals 0 into this expression that we were given. So in the I direction, we've got 0. In the j direction, we've still got 3j, and in the k direction, it's 0. So that's our velocity at t equals 0. Okay, and then part C, for this one, we're told that the acceleration is equal to 2t in the I direction plus 2j. Now, to get the velocity, we're going to have to integrate the acceleration with respect to time. And so we're doing the integral of 2ti plus 2j dt. So integrating this, we've got 2t squared on 2 in the I direction plus 2tj plus some constant. So we're told that when t equals 0, v equals 0. And so we can substitute in here. We've got 0 is equal to, putting in t equals 0, in the I direction it's 0, in the j direction it's 0, so that's equal to our constant. So once again, we've just got a constant equal to 0. So this tells us that our velocity, we can simplify this a bit, these 2's will cancel out. We've got t squared I plus 2tj. And then we need to get our displacement, which is the integral of the velocity with respect to time. So we're integrating this, t squared j plus 2t, sorry, that's an I, plus 2tj dt. And when we integrate that, we've got t cubed on 3i plus, here we've got 2t squared on 2j plus our constant. And then in this case, we're told that at t equals 0, s is equal to 2i at t equals 0. So we've got 2i is equal to, substituting in t equals 0 here, we've got 0i, and the j, that's 0, and so that's our constant. So we can simplify this a little bit. We've got s is equal to 2i plus t cubed on 3. So t cubed on 3 plus 2 in the I direction, plus in our j direction, we've got the t squared j. So we've now filled in all the boxes in that table. Okay, this is problem 3. So in this problem, we've got a spider crawling along a table, and he's attempting to jump onto a stack of magazines. So let's draw a little diagram. Here's our spider on the table. Here's our stack of magazines. And currently we're told that the spider is 4 centimeters from the stack of magazines, and it leaps up like this with a velocity of 0.870 meters per second at an angle of 35 degrees with the horizontal. And in part A, we want to know maximum height. So what happens is the spider leaps up and follows a parabolic path, and eventually we're going to be working out if it manages to make it onto the magazines here or not. So to get the maximum height, we're going to need to consider what's going on in the vertical direction, because we know that at maximum height, the velocity in the y direction is equal to 0. So we can use our kinematic equation, v squared equals u squared plus 2as. I've chosen this one because we know about the final velocity, we know about the initial velocity, we can work out the y component of that, and s is the displacement, so that's going to be the maximum height in this case. So the maximum height is here, h, which isn't necessarily aligned with the magazines. We'll be finding out where it is later. So, and ay, we know that's the acceleration due to gravity. So let's work out what uy is. We've got our initial velocity here, which is u is equal to 0.870. And then we can split this into a horizontal and a vertical component, and this is 35 degrees. So here is uy, and that's equal to 0.870 times sine of 35. And when we work out what that is, it is equal to 0.499. Then we might need the horizontal later. So ux is equal to 0.870 cos of 35, which is equal to 0.713. And these are meters per second. Okay, so now we can substitute into this equation here. So we've got 0 squared is equal to uy, which is the 0.499 squared. Now plus 2 times, now ay, that's the acceleration in the y direction is due to gravity. So this is equal to minus 9.8. The negative shows that it's going downwards because this velocity is upward, so it's positive. This is in the opposite direction. Times the displacement, which is the maximum height, h, which we're trying to find. So we can rearrange this for h. So h is equal to 0.499 squared over 2 times 9.8. And solving that on the calculator, we end up with 0.0127, which is in meters. So if we times it by 100, we'll get it into centimeters. So 1.27 centimeters is the maximum height that the spider reaches. Now in part B, it asks us how far away horizontally from its jumping point does this occur. So we're basically trying to find this length here. That's what we want. So we know that horizontally there is no acceleration. So horizontally we can use s is equal to ut plus a half at squared, except that this thing here is 0 because there is no acceleration. So horizontally the displacement is just equal to the initial velocity times the time. So if we knew the time it took to get to this maximum height, we have ux over here, so we could find this distance here. So we need to find the time. So to do that, we can use v equals u plus at, but now we're going to need to use our vertical components again because the maximum height is when vy is equal to 0. So we can put in 0 is equal to uy, which is 0.499, ay, that was minus 9.8, and this is times t, which tells us that t is equal to 0.499 over 9.8, which is equal to 0.0509 seconds. So now we can substitute into this one. So s of x is equal to u of x, which is 0.713 times the time, which is 0.50, sorry, I left off a 0, 0.0509. And so solving that, I end up with 0.0363 meters, which if I times by 100, I get into centimeters. So that's 3.63 centimeters. Part C of this question then asks us if the magazine is 0.99 centimeters tall, so this distance is 0.990 centimeters, does the spider jump high enough to land on the magazine? So we want to know, does this happen or not? So what we're going to need to know is, because the magazine is 4 centimeters away from the spider, we're going to need to know how high is the spider at 4 centimeters. So how high is spider at 4 centimeters? So if we can work out the time it takes for the spider to travel the 4 centimeters, then we can work out, using this equation with the vertical components, how high the spider is. So find how long it takes the spider to travel 4 centimeters. So in order to do that, we're going to use this equation here. So we've got s of x is equal to uxt, but this time we're trying to find t. So we've got s of x over u of x. We know that the displacement that it's going is 4 centimeters. So I've put that in meters because ux is in meters per second. So divided by 0.713. And so the time it takes to do that is equal to 0.0561 seconds. And now what I want to do is work out how high it is there. So now I'm going to use s is equal to ut plus a half at squared, but this will be the vertical components. So this is equal to 0.499 times the 0.0561 plus a half times minus 9.8, because that's downwards, times t squared, which is 0.5610 squared. And so that is equal to 0.0126 meters, which if we times by 100, we get 1.26 centimeters. So 4 centimeters away, the spider is 1.26 centimeters high, which is higher than 0.990 centimeters. So because it's higher than the stack of magazines at the start of the magazines, it does land on the magazines. So it does make it onto the magazines. This is problem 4. In this problem, we've got a spacecraft with 2 engines which are turned on for 684 seconds. And when the velocity of the craft has x components, so the initial x velocity is given by 437 meters per second, and the initial y velocity is given by 6,280 meters per second. And while the engines are firing, the displacement is in the x direction. Delta x is equal to 4.11 times 10 to the 6 meters, and delta y is equal to 6.07 times 10 to the 6 meters. And what we're asked to find is ax and ay, and we're assuming that the acceleration is constant over this period. Okay, so we have the displacement, so we have s, we have the time, and we have the initial velocity. So these are the things that we know, and what we're trying to find is the acceleration. So that tells us that probably the best kinematic equation to use is s is equal to ut plus a half at squared, because this equation uses these variables, but it doesn't use velocity. Okay, so what we're going to do is we're going to rearrange this because we're trying to find the acceleration. So to rearrange this, we can say, well, a half at squared is equal to s minus ut, and so a is equal to s minus ut over a half t squared, which we could also write, if we want, as 2 times s minus ut over t squared. So now what we can do is we can just substitute our numbers in for the x direction and also for the y direction. So a of x is equal to 2 times the displacement in the x direction, which is 4.11 times 10 to the 6, minus u of x, which is 437, times t, which is the 684, or divided by t squared, which is 684 squared. So solving that one on the calculator, we get 16.3 meters per second per second. Then we do the same thing in the y direction. So this is 2 times the displacement in the y direction is 6.07 times 10 to the 6, then minus the velocity in the y direction, the initial velocity, 6,280 times t, which is 684, and then we're dividing by t squared, which is 684 squared. And so solving that one on the calculator, we get 7.59 meters per second, and then we've solved that problem. This is problem 5. So in this problem, we're told that stones are thrown horizontally with the same velocity from the tops of 2 different buildings. One stone lands twice as far from the base of the building from which it was thrown as does the other stone. So let's draw a little diagram here. We've got a kind of tall building here with some height h. We've got a stone thrown from the top, and it travels a distance from here to here of 2x. And then we've got a shorter building here, and the stone is thrown from the top of this one, and it travels a distance x. So let's let this one here have a height little h. And what we want to know is what is big H on little h equal to. So because these are undergoing projectile motion, we know that horizontally the speed is constant. So for this one, we can write, well, x, the distance traveled, is going to be equal to ux times t, where t is the time of flight, the time it takes it to drop to the ground. So now what we can do is consider the vertical component to try and work out how long it's going to take the stone to drop to the ground. So to work out how long it's going to take to drop to the ground, let's use s is equal to ut plus a half at squared, and we're using vertical components, so let's put little y's here. Now we know that uy is equal to 0 because in the question it told us that the stone was thrown horizontally, which implies that it doesn't have any vertical component to its initial velocity, so uy is 0. So this one's 0, and we know that ay is equal to g, and it's going downwards. So we can write, well, sy, which is the height of the building, so h is equal to a half gt squared. And so rearranging this to get t, we've got t squared is equal to 2h on g, which tells us that t is equal to the square root of 2h on g. So this tells us that x is equal to ux times the square root of 2h on g. Now the only thing that's different between these two is here we've got 2x, so 2x here will equal ux times t dash, where t dash is the time it takes this stone to get to the ground. We calculate that the same way, but rather than little h here, it falls a distance capital H. So we've got t dash is equal to 2h on g square root. And so we can write for this taller building, we've got, well, 2x is equal to ux times the square root of 2h on g. Now what we're trying to get is the ratio of these two heights. So a nice way to do that is to divide this equation here by this equation here. So we can write, well, 2x on x, so dividing the left-hand sides, is equal to ux root 2h on g divided by this one, ux times 2h on g. Now there's lots of common factors here which cancel out. So the x's are the same, the ux's are the same, the g's are the same, and there's a root 2 here and a root 2 here. So this is equal to the square root of h on h. What we're trying to find is what's h on h. So we're just going to want to square this now. So we've got 2 squared, which is 4, is equal to h on h. So our taller building needs to be 4 times the height of the smaller building. This is problem 6. So in this problem, a projectile is launched from ground level at an angle of 12 degrees above the horizontal. It returns to ground level. So let's draw a little sketch. Here it is going up and back, and this angle in here, theta, is equal to 12 degrees. Now the question says, to what value should the launch angle be adjusted without changing the launch speed so that the range doubles? So let's say it had an initial speed of u here. So now we're launching it at a new angle like this, and the range is doubled. So if this was r, the new range is 2r, and let's call the new angle here phi. So what we're trying to do is find out what is phi. So one option would just be to use the range equation, but I find it fairly hard to learn all those equations. So I like to just go back and use what we know with the kinematic equations. So we know for projectile motion that it's got constant horizontal speed. So we know that r, the range here, is equal to ux times the time of flight, if t is the time of flight, and we can relate ux to u. Here's u, this is theta, and ux here is equal to u cos theta. So this is equal to u cos theta times t, where t is the total time of flight. So if we could work out the total time of flight, then we'd know the range. So to work out the time of flight, what we can do is we can work out the time to maximum height, and we know that t is equal to twice the time it takes to get to maximum height. Because as long as we ignore air resistance, it takes as long to go up as it does to come back down. It's all completely symmetric. So we can work out the time to maximum height. And to do that, we'll make use of the fact that at maximum height, the velocity is equal to 0. So we can use v is equal to u plus at, and we're going to use the vertical components in this equation to get our time to maximum height. So we've got vy, that's 0, uy, so this is the initial vertical velocity. So that's this side here, which is u sine theta. So this is u sine theta minus gt, and so rearranging, t is equal to u sine theta over g, and this is the time to max height. So maybe we'll just call it t dash or something, because it's different to this t up here, which is the time of flight. So the time of flight t is equal to 2u sine theta on g, because it's double this. So we've now got our expression for the range. The range is equal to u cos theta times 2u sine theta on g. And so we can write that as 2u squared cos theta sine theta on g. And then using the trigonometric identity, which is given in the question, we know that 2 cos theta sine theta is equal to sine 2 theta. So this is u squared sine 2 theta on g. Okay, so now what we're trying to find is this phi. So we can write, well, the range is doubled, so the range is 2r, and we've got the same initial velocity, u squared, but now the angle is sine of 2 phi over g. So this is one equation, and this is the other equation. And what we can do now is solve these simultaneously, like we did in some of the previous questions. So what we'll do is we'll divide this one here by the one over here. So on the left hand side here we have r, and here we've got 2r. So we can say, well, 2r over r is equal to u squared sine 2 phi over g, and that's divided by u squared sine 2 theta over g. And then you can see there's lots of common factors which will cancel out. So the r's cancel, the u squareds cancel, the g's cancel, and we've got 2 is equal to sine 2 phi over sine 2 theta. But we were told what theta was, it's 12 degrees. So we can say, well, sine 2 phi is equal to 2 sine times 2 times 12. And so this is equal to 2 sine of 24 degrees. And we can work out what this is. It is equal to 0.8134. So then we can find, well, 2 phi is equal to 54.4 degrees, which tells us that phi is equal to a half of this. Dividing by 2, we get 27.2 degrees. So that's a way to solve this question. And yeah, if you do know the range equation, then you could have just used that from the start. Okay, so this is question 7. In this question, imagine you're spinning around on the spot holding a bucket. The bucket is tracing out a horizontal circle. You then let go of the bucket. Does the bucket continue to travel in a circle? The answer is no, it doesn't continue to travel in a circle because you're no longer applying a force on it, forcing it to go around the circle. So if not, what direction does it go in and why? Okay, so horizontally, it travels with a constant speed in the direction it was going as you let go. Now vertically, because it's above the ground, it's going to feel acceleration due to gravity and accelerate down to the ground. So vertically, it accelerates down to the ground. So as a result, it traces out a parabolic path to the ground. So it goes, when you let go, goes like that if it's initially traveling this way. Okay, this is problem 8. So in this one, we've got a 3 kilogram mass which is being spun around a circle like this. We've got a point P here, and we're told that this is the J direction and this is the I direction, and the length of the cord is 2 meters. So this length here is 2 meters, and in 60 seconds it completes 20 revolutions. Now in part A of the question, we're asked to write down an expression for the velocity of the mass at point P in unit vector notation. So we can use that the velocity is equal to the distance, which is the circumference of the circle, so 2 pi r, divided by the time it takes to go around the circle, which is the period t. So this t here stands for period. So we're going to need to know these things to work out the magnitude of the velocity. So we know the radius that was given. What we're going to need to work out is the period. So the period is time for 1 revolution, and we know that in 60 seconds it completes 20 revolutions. So to get the time it takes for 1 revolution, we're going to need to divide the 60 seconds, the time it takes, by the number of revolutions it does, the 20. So when we divide 60 by 20, we end up with 3 seconds is the period, so how long it takes to complete 1 circle. So then we can say, well, 2 pi times 2, which is the radius, divided by 3. We could write this as 4/3 pi, or we can evaluate that, and when we evaluate it, we end up with 4.189, which we can give to 2 significant figures as 4.2. But the question asked us to write it in unit vector notation. So we're going to have to take into account the direction that it's traveling. So at point P, the direction it's traveling is like this. It's a tangent to the circle. So that is in the negative I direction. So we can write, well, the velocity then can be written as minus 4.2 I meters per second. In part B, we're asked to write an expression for the acceleration in unit vector notation. So considering the acceleration here is directed towards the center of the circle like that. So it's going to be in the negative J direction. And we know that A is equal to V squared over R. So we can substitute in, we worked out the velocity here, 4.189 squared, and the radius was 2. So we can work out what this is. This is 8.8. So this tells us that the acceleration in unit vector notation is minus 8.8 J meters per second per second. Now part C asks us, what is the magnitude of the tension exerted by the cord on the mass? So the tension is the force which is making it accelerate. So we know that the force is equal to the tension which is equal to ma, and we've got the acceleration just here. So we can say, well, the tension then is equal to the mass, which is 3, times the acceleration, which is 8.8. So this is equal to 26 newtons. This is problem 9. So in this problem, we've got the blade of a windshield wiper and it's moving through 90 degrees in 0.40 seconds. And the tip of the blade moves on an arc of a circle and it has a radius of 0.45 meters. Okay, so we've basically got the blade moving like this and the length is equal to 0.45 meters. Now, part A of the question asks, what is the period of the tip of the blade? So period is the time for one complete revolution. Now, what we've been given is the time for it to go through 90 degrees. 90 degrees is a quarter of a revolution. You need to go through 4 of those to make up a complete 360 degrees. So the period is going to be 0.40 times 4, which is equal to 1.6 seconds. Part B then asks us, what is the magnitude of the central acceleration of the tip of the blade? So we know that the acceleration, the magnitude, is given by v squared on r. So we're going to need to work out what v is. So we know that v is equal to 2 pi r over the period. So the total distance it travels divided by the time. So this is 2 pi times 0.45 and the period we found was 1.6. So solving this, we end up with a velocity of 1.767 meters per second. So now we can substitute this into this equation here. So we've now got 1.767 squared divided by 0.45, and solving this, we end up with 6.94 meters per second, which we can write to two significant figures as 6.9 meters per second. Now part C asks us, is the period the same along the whole length of the blade? Well, every point here is attached to the blade, so they all need to move together at the same time. So the period is constant. And then it asks us, what about the centripetal acceleration and the angular velocity? So let's start with the angular velocity. So the angular velocity tells us how quickly it's moving through a certain angle. Now, because it's all got the same period, it's all moving through the same angle at the same time. So the angular velocity, omega, is constant. And now the centripetal acceleration, we saw one way of writing it here, but another way to write it is omega squared r. And we can see that because omega is constant, but the radius will be different for the different points. If it's closer in, it's got a smaller radius, then the centripetal acceleration must be different. So is different as it depends on radius. So it's easier to use this equation to work that out than this one. We could do it with this one, but it's not immediately obvious how the velocity is changing. We'd need to work a bit harder at getting it out from this equation than we would from this one. This is problem 10. So in this problem, we've got a diaphragm in a loudspeaker and it's undergoing simple harmonic motion. And the simple harmonic motion has a frequency of 1 kilohertz, which is equal to 1,000 hertz. And it's got an amplitude of 0.20 millimeters, which is 0.20 times 10 to the minus 3 meters. And in part A, we're asked, what is the period of the motion? So period is the inverse of the frequency. So this is equal to 1 divided by 1,000, which we can write as 10 to the minus 3 seconds is the period, or we could say that this is equal to 1 millisecond if we want. Part B then asks, what is the maximum speed of the diaphragm and at what point does it occur? Okay, so because it's undergoing simple harmonic motion, we can write the displacement as x is equal to a cos omega t, or we could write sine omega t if we wanted. And then we've got that the velocity is the derivative of this, so this is equal to minus a omega sine omega t, and we'll need the acceleration later, so let's do that now too. So then we differentiate this with respect to time, and we end up with minus a omega squared cos omega t. So to find the maximum velocity, we want the maximum possible value that this can have. So that will occur when sine omega t is equal to -1. So V max is going to be equal to A omega, and omega is 2 pi f. So this is A times 2 pi f. And these are all things that we were given in the question. So now we can just substitute in. So we've got 0.20 times 10 to the minus 3 times 2 pi times the frequency, which is 1,000. And solving that on the calculator, we end up with 1.3 meters per second. Or alternatively, if we want, the 1,000 here will cancel out the 10 to the minus 3, so we could also write it as 0.40, because 0.2 times 2 gives 0.40 pi would be another way we could write that. And it also asks at what point does this occur. So in simple harmonic motion, the maximum velocity occurs in the middle when the displacement is 0. So this occurs in the middle of the motion, where the displacement from equilibrium is 0. Then part C asks us what is the maximum acceleration of the diaphragm and at what point does it occur. Okay, so we've got our equation for the acceleration here. So this is going to have a maximum value when minus cos omega t is equal to -1. So we'll have that the acceleration, the maximum acceleration, is equal to a omega squared. So that is equal to 0.20 times 10 to the minus 3. And then omega is just 2 pi f. So this is 2 pi times 1,000, and that's squared. So then putting that into the calculator, we end up with 7,896, which is equal to 7,900 meters per second per second. Now it also asks us where does this occur. So the maximum acceleration occurs when it's changing direction at the edges. So this occurs at the edges of the motion, where the displacement from equilibrium is maximum. This is question 11. So in this one, we've got an object attached to a horizontal spring oscillating backwards and forth. So something like this. If we've got a wall there, here's a spring, here's our object, and it's moving backwards and forwards like this. And we can say it's got no displacement here, and here it's got the maximum displacement, so the displacement is equal to the amplitude. And we're told that the maximum speed, V max, is equal to 1.25 meters per second, and the maximum acceleration is equal to 6.89 meters per second. And we're asked how much time elapses between an instant when the object's speed is at its maximum. So that will be here. So speed max. And when its acceleration is at its maximum. So that's here. So acceleration max. So for one complete period, it goes here, it goes back here, and then it goes back here. So you can see that the time between here and here, what we're looking for is 1/4 of the period. So looking for 1/4 of the period. Okay, so we want to try and find the period somehow. Now to do that, we can remember that the displacement for simple harmonic motion is given by x is equal to a cos omega t, or we can use sine omega t if we want. And so the velocity is given by the derivative of this, which is minus a omega sine omega t. And the acceleration is given by the derivative of this, which is minus a omega squared cos omega t. So from that we can see that V max is going to happen when sine omega t is minus 1, so this will be a omega, and a max will occur when cos omega t is minus 1, so that's a omega squared. So what's nice about this is we can now say, well, a max over v max is equal to a omega squared over a omega, which you can see is equal to omega, but we can evaluate this because we've got a max at 6.89 and we've got v max, it's 1.25. So when we evaluate this, we end up with omega is equal to 5.512 radians per second. And now omega we know is equal to 2 pi f, where f is the frequency, so that's 2 pi divided by the period. So we can rearrange this and say, well, the period then is equal to 2 pi over omega, so that's 2 pi over 5.512, which is equal to 1.14 seconds. But what we were looking for was 1/4 of the period, so now we just need to divide this by 4, and that tells us that the time is equal to 1.14 on 4, which is equal to 0.285 seconds. So now we've solved that problem.